So, let us carry on with the solution of these equations, numerical solution of these equations. We have seen two methods, namely the bisection method and the second method. We saw that the bisection method suffers from the fact that first it has slower convergence, it is a linear convergence, and the other one is that you have to give two values which subtend the root. If you miss the root and give two values which they do not subtend the root, and in that case bisection method will not work, and in fact you have to give again new choices. The second method is slightly better, which requires you to which has a faster convergence, faster than linear convergence. Now, let us look at the Newton-Raphson method. So, what is this method? How do we use it in order to calculate the root of a given equation? Okay. It of course requires only one value to guess. So, it starts with just one value, and so let us just consider the following graph for f x. So, this is your f x. Okay, so, this is f x as a function of x, and let us take a value, let us call this value as x 1, that is the guess value, and what it requires is that you need to calculate or rather draw the tangent at this point, and not a very good tangent, but that is just a freehand drawing. It just touches at this particular point at x 1, and then let us call this angle as theta, and then of course we get, so wherever the tangent cuts the x axis, let us call that point as x 2, and take this point f of x 2, which is here, and then draw another tangent and so on. Okay. So, if you see that we are coming closer to the root, and so it requires the value of the function at a given guess point, and then requires you to calculate the slope at that particular point. Okay. So, this is how we come closer. You see x 1 was the guess value, and then it became x 2, and then it became x 3 and so on, and of course, it also has limitations which we are going to come to, but this will be shown to have a faster convergence as compared to the bisection or the second method. So, so take any point, I am writing it for your convenience, any point, let us call it a guess point x 1, that is a value of x, then draw a tangent at x 1, then of course, let it intersect x axis at x equal to x 2. Now, the slope of the tangent line which is nothing but tan theta, this is equal to f of x 1 minus x 2. Of course, it is f of x 2 as well, but then f of x 2 is equal to 0. So, this is equal to 0. So, we can simply write it as f of x 1 and x 1 minus x 2. Okay. F of x 2 is 0 because you see that the function is cutting the line at x 2 at exactly x equal to x 2. So, this is the so that is the value of this, or rather that is the slope of the tangent line. Now, if you solving for x 2, one gets x 2 equal to x 1 minus f of x 1 divided by f prime of x 1, and this is precisely called as the Newton-Raphson, and in short we will call it as a NR formula. Okay. So, this is the iteration formula. So, what it means is that, so if you iterate it, x 3 becomes equal to x 2 minus f of x 2 divided by f prime of x 2, and hence basically you get a new root after every iteration, which is equal to the old root minus the value of the function at that old root point, divided by the slope at that particular point. So, this is so if you iterate it, your x I plus 1 or x n plus 1 if you like, it is equal to x n minus f of x n divided by f prime of x n. So, let us box this and we will use this like a NR formula. It is the same as the above, excepting that it is written for after n iterations. Okay. So, this is the value of the new root. Of course, there could be a problem. The problem occurs when f prime of x n goes to 0. Okay. So, if that happens, that is this goes to 0, then of course, you see the denominator becomes 0, means it blows up. So, you would not get any, so you will get an infinity for the new root, which is of course not an allowed solution for a given problem. So, in that case, one has to go back and look for a new guess. And iterate the process again. So, let me quickly take you through this thing, that you have a curve and you want to know the solution of that equation. It could be highly nonlinear. You need to make a guess, and of course, you need to make also a tolerance, because once the actual root is reached, or if you are doing it several times the iteration, you have to understand that when to stop that iteration, and that you have reached the final answer for your particular question that you are attending to. And in order to do that, your x n plus 1 minus x n should give you a tolerance number. If the x n minus 1 minus x n, the modulus value of that or the absolute value of that falls below the tolerance, then you say that I am done with my numeric computation of the root, and that is the value of the root, either x n or x n plus 1. So, that you need to give a tolerance. We are just going to come to that. So, let us look at a simple example. Says calculate root over 2 by Newton-Raphson method. So, that of course tells you that you have f x equal to x square minus 2 equal to 0. So, that you have to solve this equation in order to find the value of square root of 2. Now, of course, this gives that the f prime x is equal to 2 x. Okay. So, if I take guess as 1, that is your the first value that which we have taken, say call it x 1, or you can call it x 0, that is the 0th value, it is equal to 1. Then what we can do is that we can calculate x 1, which is equal to 1 minus f of x 0, which is 1, and f prime of x 0, which is this, which is f prime of 1. So, it is 1 minus f of 1 is equal to minus 1, and f prime of 1 is equal to 2, because if you put x equal to 1 there. So, this becomes equal to 1 plus half, which is equal to 1.5. So, that is the second in the second iteration you get a value which is 1.5. If you want to iterate it further, if you feel that the value has not reached, you know the value, this is like 1.414 etcetera, and then so basically this is very well known 414 with, I leave those extra digits here. So, now your x 2 will simply be equal to x 1 minus f of x 1, which is 1.5. So, let us write 1.5 in that case, and this is 1.5 divided by f prime at 1.5, and this comes out to be 1.41767. Similarly, if you iterate, your x 3 becomes equal to 1.41. Please check these numbers as you practice this, and then again doing it 1, it is 414,214, and it is pretty much accurate till 6 decimal places. So, we can take this x 4 to be the root for. So, so, that gives you only 3-4 iterations. Of course, the problem is very simple. So, it gives you a root in only in something like 3-4 iterations. It gives you a value which is fairly reliable and very close to the exact value. So, let us look at the algorithm of this Newton-Raphson method. So, the first thing is that assign an initial value of x, that is x 0, and tolerance, let us call it TOL. So, this tolerance will decide when to terminate the numeric computation of the root. Okay. So, this is that reason for the tolerance. So, these are steps. So, let us call them as steps. So, step 1 and then step 2 is that of course, evaluate f of x 0 and f prime of x 0, that is at the initial value. And then obtain an improved estimate of x 0 by using NR formula. And so, this will become equal to x 1 equal to x 0 f of x 0 divided by f prime of x 0. So, along with that of course, you should check accuracy, that is the two successive values whether they are or the relative values are coming closer or lesser than the tolerance, which means that check for x 1 minus x 0 divided by x 1, the absolute value of that whether it is falling below the tolerance, okay, TOL. And if it is yes, you stop, okay, and if no, go back to step 3 and then of course, stop once you find that this condition is met. So, this is the simple algorithm of this method. It is fairly easy method, however, and it has lots of merits. So, let us look at an example, another example of this Newton-Raphson method. These are simple examples, but these simple examples are nevertheless very indicative of the efficiency of the method. So, let us look at this equation, which is it is exponential minus x minus 5 x equal to 0. So, what we have been given is that this is equal to minus 5 x, okay, and that of course gives me that f prime x, which is the slope or the derivative, which is equal to minus exponential minus x n minus 5. Okay. So, what is my x I plus 1? That is equal to x I minus exponential minus x minus 5 x divided by minus exponential minus x minus 5, and this tells you that it is equal to plus exponential minus x minus 5 x divided by exponential minus x plus 5 and so on. So, this would be the formula for iterating the roots, and then you take a value of guess value, initial guess value for x, and one would get successive values, and then you also decide on a tolerance and find that, I mean, check for the relative difference between the two roots or in two successive iterations, and if you find that that value is falling below the tolerance or falling lower than the tolerance, then the computation is complete. Okay. So, let us give another example, which are sort of is a quantum mechanics. One often encounters this, and sometimes even students have difficulty with the quantum mechanics question itself, not with regard to solving it numerically, but with regard to understanding that what bound states etc. mean. So, let us give an example. So, let us take a potential well it's not a potential barrier, it's a finite potential well of some certain width, let's call it from minus A to plus A, with the 0 lying in between, and this has a value equal to, call it a V 0. There is a region 1, this is the inside of the well, that is called region 2, and it is region 3 is here. Suppose you have an energy which is lower than, so your E is actually lower than V 0, and of course, your V 0 is negative here. So, this is V equal to 0 rather. And we can solve this problem. It's a so we can solve the Schrodinger equation. Just to remind you, is written as this, and it's a d2 psi dx2 plus a v of x psi of x. So, let us call it a psi of x. It's a one dimensional problem, and this is equal to a E psi of x. Okay. So, it's quite simple to solve. The potential is 0 outside, and it's equal to minus V 0 inside, and see, in region 1 and 3 one can put the potential equal to 0, and in the region 2 the depth is V 0. So, we can call these and the energy of the particle is actually lower than the magnitude of this, or let us call it this, and so on. I will not go through the details of the solution, I will simply write down the solutions themselves. So, this particular will become equal to, so 2 m d2 psi dx2 plus 2 m by h cross square V 0 minus E and psi, and that is equal to 0. So, we have a solution as psi 1 equal to c exponential beta x and d exponential minus beta x, beta being this constant for a given energy, psi 2 where alpha is another constant which is given by, you should be able to find it in any quantum mechanics book, say for example, Griffiths, or even I mean any book, any quantum mechanics book will give it. Psi 3 has a solution which is similar to 1, except the fact that it does not have a reflected component such as 1. So, it is in 3 it is like, okay, and one can apply the boundary conditions. At plus and minus A, maybe there is a minus sign here, and what one gets is the following. I am simply writing down the equations that are needed for us and how to arrive at those equations. So, at x equal to minus A, so these are psi being continuous and d psi dx being continuous. And these are at x equal to plus A, Okay. This problem of course has a finite parity. Parity means the inversion symmetry, which means that because of the symmetry of the potential, if you see the potential is symmetric about 0. So, if this is called as an inversion symmetry or a parity, and if the potential has that symmetry, the wave functions actually pick up or rather pick up that symmetry, and they split into two classes of solutions. One is called as the even parity states, and the other is called as the odd parity states. And so the wave functions have different parity. So, the even states correspond to A equal to 0, B not equal to 0, C equal to F, that implies C equal to F, and it implies alpha tan alpha A equal to beta. And the odd states, we are coming to the interesting part of the question which we have to solve. This corresponds to A not equal to 0, B equal to 0, C equal to minus F, and this is equal to alpha cot alpha A equal to minus beta. And you see this in your quantum mechanics book. Let's just go to that. Why for even states you will have A equal to 0? Because your solution is the A goes with a sign. Now, if x changes sign, sign changes sign as well, right, because sign is an odd function, cos is an even function. So, for even states we want the odd term to go to 0. So, that is why A equal to 0, but B being associated with the cosine term, and cosine being even, that is if you change x to minus x, cosine does not change sign, which means cos of minus theta equal to cos theta. In that condition, of course, applying the boundary conditions, your C becomes equal to F. And what we get by from these two conditions is that the alpha tan alpha A equal to beta, and similarly for the odd states, when you want the even terms to go to 0, C acquires a value equal to minus F, and similarly the bound states are given by these conditions. So, we have two equations which we want to So, we have an alpha tan alpha A equal to beta, and we have a alpha cot alpha A equal to minus beta. Remember your alpha equal to root over 2 m e by h cross square, and beta equal to root over 2 m by h cross square v naught minus e. So, you have to solve for that is the whole idea of a quantum mechanical problem, that we have to solve for the energy, and if you have to solve for the energy, you see energy is there in both alpha and beta, and it is not only there in alpha and beta, and since alpha and beta occur at both sides of the equation. So, there are you cannot simply separate out the unknown on one side and writing all the known quantities on the other side. Both the sides of the equation on either side of the equality sign, it involves these energy E. So, solving is somewhat non-trivial, and also given the fact that this alpha is present in the arguments of both tan and cot, tangent and cotangent, and that makes the problem even more difficult. So, the books you see the books in which they do it, these are called as transcendental equation, and the only solution that is possible, or rather the only two methods that are possible, one being the graphical solution. So, let me plot for a given value of energy, let me plot both the sides separately and see where they intersect. Okay. And so, basically this is what you will see. that there are tans etc. and so on, and this beta will of course, if you plot it, I mean suppose you plot that thing and say it goes like this. So, this is the say RHS. Okay. So, you get a solution here at the origin, then you get a solution here, and then you get a solution here, and then you get a solution here. So, your energy of the particle will decide how many bound states are there. Okay. So, you may not have a large number of bound states, whereas, for the other solution, this is for the even solutions. And for the odd solutions, because they involve cotangent, cotangent does not pass through the origin. So, you have so basically you will have again these as these values. So, one very trivial information that comes out from this is that if you have infinitesimal energy, that is if E is very small and negative, you still have an even bound state. If you go to that, if your E is infinitesimally below 0, you still have the possibility of at least one bound state, which is even bound state, which if you the wave function has a property that if you change x to minus x, it does not change sign, that is called evenness. And but if you look at this plot, you will not have a solution for an infinitesimal, you will not have an odd bound state, that is it will change sign on changing the sign of x, it will not have such a bound state for infinitesimal small infinitesimally small energy. Which are fine, of course, we have learned that, and this is called a graphical solution. But what about solving these equations using the numerical method that we have been exposed to for or using Newton-Raphson's method? Of course, for a computer, it is more convenient to represent it as, I mean the equation as the reason being that there are divisions by sine and cos. So, we can simply write it as beta cosine alpha a equal to alpha sine alpha a for the even bound states. I hope this word even bound state is not bothering you. Once again, I want to repeat, it is a solution of this Schrodinger equation for the particle, which has a property that if you change x to minus x, the wave function does not change sign. That is called as an even bound state or even wave function. So, that bound state corresponds to a wave function, and that is the function that we are talking about. It is a simple function. I mean, wave function is a quantum mechanical concept. For us, it is a simple function. So, these are simple functions, and beta and alpha actually contains E within a square root. And for the other odd bound state, which of course, you know that it has a meaning that this is, if you change x to minus x, then it will change sign for odd bound states. So, we could have started this problem here, that take these two equations and find out the roots of these equations, but we wanted to give put it in perspective. I mean, this is basically very important for the physics students to know that this calculation of bound states, because scattering states are easier when you have a potential infinite potential well and things like that. Things are easier where you have solutions which are of sine and cosine, but when you have these other kind of solutions, then you have these bound states. And so, to cast it in the form that we need to, so let us only do it for the even bound states. F of E beta cosine alpha A minus alpha sine alpha A, and I would get a value of E, the first iterative value of E from a guess value E 0 by calculating f of this divided by f prime of this. Okay. So, you can iterate it according to the Newton-Raphson, this equation, and the you will iterate it a number of times, and also of course defines a tolerance, so that you know when the root is reached. So, basically we will have a E I plus 1 minus E I divided by a E I plus 1, that is the relative value should fall below a predefined tolerance, and that tolerance of course depends on how accurately you want to get your root, or depends on the particular problem that you are attending. Let us look at the convergence of the Newton-Raphson method. We are testing this every time, a convergence, what is the error, how the error is reducing as you go from one iterative step to another iterative step and so on. And this is extremely important in the context of numerical method, where we need to make sure that we are doing the iterations and the errors are not increasing, they are in fact going down, and how the errors are decreasing as we go from one iterative step to another will decide what is the most efficient algorithm for a particular problem to use. And so, these are demonstrating the fact that which method out of the three that we have talked about, namely the bisection method, the second method, and the Newton-Raphson method, which one is more accurate. So, in order to do this, let us look at the at the nth step, x n is the estimate for root of a function f of x and of an equation f of x equal to 0. Okay. Now, if x n and x n plus 1 are close to each other, so we are assuming that the two computed values for the root in two successive iterations after a number of iterations, they do not differ too much, then use Taylor series, which I believe you have read in your course of mathematics or even in some parts of statistical mechanics and physics, or in different branches of engineering, which is done to expand a function about a value which is a neighboring value. So, f of x n plus 1 is expanded about f of x n I will tell you what is R. And then there are other terms, but since x n is sufficiently close to x n plus 1, I am stopping it at the quadratic level of this series. R is any point between x n plus 1 and x n. Because they are close, we can take the value at any point in between these two values and compute the double derivative at that point. So, there is a x n that I have missed. All right. So, the thing is calculated, or rather the slope is calculated at x equal to x n. Now, let us assume that the exact root is x r, r for the real root or something. Also assume that x n plus 1 is very close to the real root x r, so that we can claim f of x n plus 1, which is equal to f of x r equal to 0, because if it is a root, then of course, the value of the function will vanish there. Now, importantly, x n plus 1 and x r are two different points which are neighboring, very nearby points, but the values of the function at those two particular points, that is x n plus 1 and x r, the values are same, but the points are not same. That is what this is saying. So, if your f x n plus 1 is equal to 0, let us call that as equation 1, putting f of x n plus 1 equal to 0 in equation 1, we get 0 equal to f of x n plus f of x n plus 1 minus x n plus half of f r x n plus 1 minus x n square, and we are neglecting terms from there on. All right. Now, so let us call this as equation 2. From the Newton-Raphson formula, let us write it as NR as a brief. So, f of x n equal to f of x n f prime of x n into x n minus x n plus 1 is the same formula that we have written earlier. X n plus 1, this is that x n plus 1 equal to x n minus f of x n divided by f prime of x n. So, this I have rearranged this to write it in this fashion. So, let us call that as equation 3. So, put 3 into and we have a 0 equal to f prime of x n minus x n plus 1, or we have this is equal to your n plus 1 from this, and a plus f prime x n, that is coming from the second term here, this one. So, this is equal to a x r minus x n. Remember, we have taken x n plus 1 equal to x r, and then we have the harmonic term, which is 2, which is actually 2 factorial, and minus x n whole square. So, if you simplify this, this becomes equal to f of x n x r minus x n plus 1. As I said, these 2 points are not same, but the values of the function at these 2 points can be taken to be same. These are 2 neighboring points, and we also have the f r, the double derivative of f evaluated at r, and this is x r minus x n whole square. So, of course, we have not substituted this to be equal to 0, but we have taken this, if you look at it, we have taken this x n plus 1 equal to x r in the second equation, but or in the second term, but have not taken in the first term, we have still considered x r and x n plus 1 to be different, but this is what we actually call as the epsilon n plus 1, that is the error at the n plus 1th step, and this we call as the error at the nth step. And it is very intentional to keep these things, because these are errors, these are extremely small quantities at the n plus 1th level, and in order to find a relationship between the error at the nth level and the n plus 1th level, we have taken these things, that is, we have this x n plus 1. So, here the x n cancels, and one has a x r minus x n plus 1, which have not taken to be the same. However, in the other, where there was x n plus 1 and x n, then we have taken x n plus 1 as x r, which is equal to x or rather it has to be the other way around. So, let us just epsilon n plus 1 equal to x r minus x n plus 1, epsilon n equal to x r minus x n. So, this tells that 0 equal to f of x n epsilon n plus 1 and plus f this and epsilon n square, there is a factor of 2. So, epsilon n plus 1 is minus the double derivative of the function evaluated at that r point, which is between x n and x n plus 1. It does not matter, you can calculate it at any of these. Anyway, these are number, this particular this is just a number. So, epsilon n plus 1 goes as epsilon n square. So, it is a quadratically convergent. Let us look at what it actually means, something to be quadratically. So, something being quadratically convergent implies that the number of correct decimal places doubles after every iteration. Okay. So, if at a particular iteration the number of correct decimal places, correct means compared to the real root, is 2, in the next it will be 4 and so on. Okay. So, that is what it means. So, of course, superior to both bisection and second method. Bisection has a linear and second has more than linear, but of course, that is not yet, I mean not power of 2, less than a power of 2, it is between 1 and 2. Okay. So, what are the demerits of NR method? Of course, which is very simple to understand, it cannot handle multiple roots. What it means is that if you have a function which goes like this and so on, so you have 3 roots. So, you have to have, you can only handle one root at a time. The other is mainly related to the divergence of f prime x n at the point of inflection. The third could be oscillatory roots. That is, if you have a situation which has a value like this, then a guess value here would give a slope here, and then you have to consider this point where it touches, and then you will get a slope which is here. So, here the roots actually oscillate. So, this is say x n and this is x n plus 1, they are completely in the different directions. And of course, this is this oscillatory solutions will cause confusion and will not let it converge. And of course, the convergence is only quadratic and not powers greater than this. We could carry on with some examples, more examples on this, or we could go and talk about the curve fitting or the interpolation, which also forms a very basic computational tool and is widely needed in order to understand the behavior of a function close to a point that is important for your problem. So, one needs to fit it, and there are lots of fitting algorithms, and we will again see a few fitting algorithms as representative methods for these curve fitting exercise.